The purpose of this video is to show you how to handle the assigning spectral portions of your Organic 2 lab reports. What I'm going to do is I'm going to go into this practice assigning spectra as a student. And what you'll see in here are questions that relate to mass spec, proton NMR, carbon NMR, and infrared spectroscopy. Let's first of all look at the mass spec portion. What we learned about mass spec was that when you put a compound into a mass spectrometer, it breaks apart into predictable fragments. In this case, we're asked to put in the molecular formula of the ions responsible for the peaks at 77 and 105. We're told to use the following order: CHO with a plus at the end, because what we're looking at are fragmentations that turn into ions. And we're given a formatting example as well. So for 44 it would be C2H4O plus, for example. Right, but we're looking at methyl benzoate, and we're looking for the peaks responsible for 77 and 105. So here's how we should handle that. First of all, we should draw what it looks like. Now this is methyl benzoate. Of course, the structures for all of these will be in your lab manual. Alright, so that's it there, and what we know is that we can expect to see cuts between CC single bonds, CO single bonds, and CN single bonds. So following that logic, we expect to see a cut here, here, and here. Now all that's left for us to do is to identify what these cuts here will represent and which fragments they'll produce. So if we cut it here, we'll get a fragment that's going to be 121 and then 15. Now the way I'm getting this, of course, is to just add up everything that's on each side of this squiggly line. So here we've got 15, which is 12 plus 3, and the rest of this is going to be 121. Of course, the whole thing weighs 136, so that's the other way that I can get the 121 as well, is to subtract 15 from 136. This cut here is going to be 105 and 31, and this one here will be 77 and 59. Alright, so remember what we were looking for in the question was the 77 and the 105. Now the 77 would be everything that's on this side of the cut, which would be C6, so 77 here, equals C6, H5, and then we put a plus at the end. Remember that the formatting was, goes C and then H. That's what it said in the question. Now the 105 is going to be everything that's on this side of the cut. Remember, this is 31. This is 16 plus 15 is 31. The rest of this must be 105. So 105 would be C7, because this is 6 and that's 7. Then we've got H5 over here, and then we've got an oxygen as well, and with a plus at the end. Now what you should do is probably just double check and make sure that these do add up to what you're talking about. So this would be 6 times 12, which is 72, plus 5, which is 77. This is 7 times 12, which is 84, plus 5, which is 89, plus 16, which is 105. So we can see that what we've got here is actually what it should work out to be. Alright, so continuing on with this, we go ahead and we can answer those questions. So we said it was C6H5 plus C7H5O plus, and those should be the correct answers for those peaks, 77 and 105. Right, next we go on to the Proton Nmr portion of things, and what you can see here is that the peaks have been labeled A and B, and this A here refers to this group of peaks, and B refers of course to this peak here. Now it says match the peaks to the appropriate number on the structure. A letter may correspond to more than one number. So here are the numbers that we're talking about. And I think the best way to approach this is to handle the numbers one at a time and try and figure out to which peak they belong. So for number 1 and actually 2 and 3, they're all part of peak A, while number 4 here is going to be for peak B. Now I'll know this because I've got my correlation chart in front of me and I know where these different peaks are expected to appear. Plus I'm using clues like the fact that the Me represents a CH3, so the 3H matches that. So this is all just the standard stuff that we've done with assigning Proton Nmr spectra. So the way to handle this is to just use the drop down here, and for 1, 2, and 3 I'll pick A, and that's what I meant by a letter referring to more than one, corresponding to more than one number, and that would be B right there. So that should be correct for that. Now for the carbon 13, we treat that in a similar fashion. Again, we have to match the peaks to the appropriate number on the structure. A letter may correspond to more than one number, same kind of deal as before. Alright, so using our knowledge of carbon 13 NMR spectroscopy, we can figure out what each of these is going to refer to. And again, what we should do is we should figure out how these correspond to the peaks. So first of all, I'll look at 1, and I can see 1 is going to be a aromatic carbon, and it's going to be in this region according to the correlation chart. Now you'll notice that there are a number of doublets here. These each have one hydrogen on them, and we can actually distinguish a little bit between them. What we know about these two, 2 and 3 relative to 1, is that there's 2 2s and 2 3s, so I would expect that those might produce higher peaks than this one would. So you've got B, D, and D. I would say that B would refer to 1 and that D would refer to 2 and 3. Now I can't say which is 2 and which is 3, just that they both belong to these two peaks here. And I'm just basing that purely on the height, the fact there's 2 of these versus 1 of these. And next we can look at 4, and 4 would be a singlet, and it would be a singlet that's in the aromatic region, so that's going to be C. 5 will be a carbonyl, which is going to be down in this region, that's going to be A. And then we've got the methyl group, which is going to be down here, and that's going to be E. Alright, so that's how you handle those kinds of assignments. Alright, so take a look now at the infrared spectrum. And what we know according to the correlation chart on the infrared spectrum is that above 3000 we're going to have peaks responsible for C double bond C's with, H is connected to C double bond C's, and this one H is connected to C single bond C's. Now on this side you've got the H is connected to C double bond C's, and it says here the group most likely responsible for the peak at 1, which is clearly above 3000, is most likely. Now it's going to have to be a CH stretch because this is where the CH stretches appear, and again this is definitely from the correlation chart. And you've got a choice here, you've got CH alkyl or CH alkenyl or aryl. So those are really the only two choices, so it's going to be between C and D. Let me give you a little bit more clarification of this. Now when I talk about CH alkyl, what I'm talking about is CH connected to a C single bond C. These typically appear between 2900 and 3000 wave numbers. When I talk about CH alkenyl or aryl, what I'm talking about are CH's connected to C double bond C's, and those typically appear between 3000 and 3100 wave numbers. So if we're talking about The group most likely to be responsible for peak 1, this is a peak above 3000, it's going to be CH, alkenyl or aryl. Likewise for 2, it's just below 3000, so we're looking at CH, alkyl. Then it's asking the group most likely responsible for the peak at 3. Well, that's 1750. It's a very strong peak. That's in the C double bond O range. The other thing that helps us out here is the fact that we already know what the structure is, and we expected to see a C double bond O, and we expected to see a CH alkyl, and we expected to see a CH alkenyl or aryl as well. So just doing the structure up again. So you should use the structure you have to make those things possible. So you've got your CH alkyl here, you've got your CH alkenyl or aryl here, and then you've got your C double bond O here. Just remember that when we talk about aryl, we're talking about hydrogens on an aromatic ring. Alright, so that's it. Good luck.